All right, guys, so we've talked about recursion using linear or arithmetic models. We're going to do recursion using exponential growth and decay today. So let's go ahead and take a look at that. So it says different balls bounce at various heights depending upon things like the type of ball, the pressure of air in the ball, and the surface on which it is bounced. The rebound percentage of a ball is found by determining the quotient of the rebound height, that is the height of each bounce, to the height of the ball before that bounce, converted to a percentage. We're going to collect data on a bouncing ball that shows the maximum height of at least 5 bounces of the ball. Then make a scatter plot of the minimum height as a function of the bounce number. Let bounce 0 be the initial drop after the drop height of the ball. So if you want to, you can do this on your own and actually kind of, do the actual thing, but I'll go ahead and give you some numbers. If you were to bounce like a bouncy ball or something, just kind of giving some examples right now. So if my initial bounce was 3 feet, the second bounce is not going to be equal to 3 feet, right? Because if you bounce something, you're gonna drop something, it bounces, comes up, comes down, comes up, comes down. You see, it's gonna get lower and lower and lower and lower until eventually it actually just stops bouncing and it's on the ground. So it's never going to be you drop it, it comes up, and it's just going to always have the same height, right? That doesn't happen. Gravity happens instead. So what we're going to do here is if our initial height was 3 feet, then bounce number 2, we're going to say is it's 2.28 feet. This is just an example that somebody actually did where they got the bouncing of some specific ball. I don't even know if it was a tennis ball or a bouncy ball or whatever, but these are the numbers that we've got. And it would be 1.74 feet for the next one, 1.33 feet for the next one, 1.05 feet for the next one, and 0.81 feet for the next one. Okay, so you can see that number's always decreasing. And so then let's go ahead and draw a scatter plot of this. And so notice right here, it's got my x-axis labeled as bounce right here. It says bounce, and then it's got 5 right here. So it's going to be bounce 1, 2, 3, 4, 5. And then it's got my height here for my y-axis. So that initial bounce of 0 is going to be right here at 3. And then my next one, my first bounce is 2.28, so I'm going to be about here. And then bounce 2 was 1.74, so about 1.74, it's about here. Next one would be 1.33, which would be about here. Bounce 4 was 1.05, so it would be just above the 1. And then 5 is 0.81, which would be just below it. So I've got this kind of graph going here. All right, that's just of that. Now, if you notice right here is it's important to go ahead and make sure that bounce number is that 3 feet. That's going to be where you're dropping that from a certain height or whatever, or it would just be the initial bounce. So if you're dropping it from somewhere, that's going to be that initial amount right there. All right, so find the average rebound percentage for your ball. So using those exact same numbers that we just used, so let's transfer those down. So I've got 3, 2.28, 1.74, 1.33, 1.05, and 0.81. And all of these are in feet. In fact, I'll go ahead and just write that. So I'm making sure we're not getting confused about any of this. All right, and so to find the average rebound percentage for the ball. Now, remember, it says up here, okay, the rebound percentage of a ball is found by determining the quotient of the rebound height, that is the height of each bounce, to the height of the ball before that bounce. Quotient, that's a fraction. So it's saying I take whatever height I have for this rebound, and then I'm going to divide it by the rebound height of the one previous. And then I'm going to convert it to a percentage. So right here with this particular one. So what I'm going to do is I'm going to take the current bounce, which was 2.28, and I'm going to divide that by the previous bounce to it. So 2.28 divided by 3. And then I've got to turn it into a percentage. So this is going to get me some sort of decimal number, and I'm going to turn it into a percentage, so I have to multiply by 100. And when I do that, I get 76%. So if I compare 2.28 to 3, 2.28 is 76% of 3. That's what that's saying. So my bounce was 76% of the initial height. So the next one, I have 1.74. So I would do 1.74, and I would divide that by the bounce previous. I'm not dividing by 3. I'm going to divide by the 2.28. It's the one immediately before. So I'm comparing how much did this second bounce compare to the first bounce. Well, if I do 1.74 divided by 2.28 and I multiply by 100, I get 76%. Okay. Then I'm going to do 1.33 divided by 1.74 times 100. And I'm taking the 1.33 and dividing by the term previous. And that would also get me 76%. Okay, so then I've got this next one, 1.05 divided by 1.33 times 100. And that's going to get me 79%. Okay, there we go. It's not exactly the same every time, but that's because math is not always going to be perfect in the real world. And then let's look at this next one right here. Then I'm going to do 0.81 divided by 1.05 times 100. And that would get me 77%. Okay. So the average rebound percentage for the ball. That means I need to go ahead and take all of these rebound percentages, so all of those numbers there, and find the average of them, because those are my rebound percentages. So I'm going to go 76 plus 76 plus 76 plus 79 plus 77, because remember, taking an average means you add up all of the numbers and then divide by how many numbers did you add up together? I added up 1, 2, 3, 4, 5. So I divide by 5. So when I take all of that and put it in the calculator, I get back 77%. So our average rebound percentage was 77% of that ball. Okay? All right, so let's look at this next one. It says tennis balls are sealed in a pressurized container to maintain the rebound percentage of the balls. A tennis ball has a rebound percentage of 55% when it is taken out of the pressurized can. Suppose the tennis ball is dropped from a height of 2 meters onto a tennis court. Use the rebound rate given to predict the height of the ball's first 7 bounces. So it goes ahead and tells me I've got bounce 0, so that's that initial height, and that's going to be that 2 meters that we were given. We were given that right here, that 2 meters. Okay, so then this next one right here, it tells me, where did I find right here, 55%. Tennis ball has a rebound percentage of 55% when it's taken out of the pressurized can. So what I'm going to have here is I'm going to find this 2 meters, and I'm going to find what is 55% of that. So that's going to be 2 times 0.55. So remember, 55% written as a decimal would be 55 divided by 100, and that gives me 0.55. So my rebound height should be 1.1 meters. All right, next one, I'm going to take that 1.1, and I'm going to also multiply that by 0.55. Because it is 55% of that bounce. So if I bounced to 2 initially, or I dropped from 2 initially, and then I bounced 1.1 meters, so the next one is going to be 55% of that 1.1. And that would be 0.605 meters. Next one, I'm going to do 0.605 times 0.55. I need to find 55% of this 0.605 meters. and that would be 0.333 meters. My fourth one, I'm going to take the 0.333 and multiply that by 0.55. Again, 55% of the previous one. And so that's going to get me 0.183 meters. All right, then this next one, I'm going to do that 0.183 times 0.55. And that's going to get me 0.101 meters. And then 0.101 times 0.555, or 0.55, sorry, gets me 0.056. And then the very last one, 0.056 times 0.5, that's going to get me 0.031 meters. So at this point in time, it's almost just hanging out on the ground there. I mean, it's still got a bit of a bounce, 0.03 meters, but not much. So that's how you would do that. If I was given, in this case, the rebound percentage and an initial height, you're just going to take that initial height and continuously, repeatedly multiply by the rebound percentage to whatever is the previous height. All right, write a recursive rule for the height of the ball for each successive bounce. Well, let's look at that. So recursive rule, remember that that is where we're going to have h of n plus 1 is equal to h of n, or sub n. And then the value that is going to be here is going to be whatever is being multiplied here. If you notice, I'm taking the previous term, and I'm multiplying it each time by 0.55. So times 0.5. I'm going to make that 0.55. Just so it's a little better. And then my n values are equal to 0, 1, 2, so on and so forth. And then my initial amount, h sub 0, would be 2, because the initial height is 2. That's my initial height. And each bounce, that's what that n value is, that 0, 1, 2. It's going to be that bounce. And then so what I'm doing each time, if you notice, all of these right here match what this little rule is. And that's what you're kind of seeing in this process. Okay, so next part here is describe in words how the height of each bounce is calculated from the height of the previous bounce. Well, the height, helps if I have the right writing to it. The height of each bounce is 0.55 times the previous. Okay. All right. Next, enter the bounce height data into your graphing calculator and make a scatter plot and then sketch the graph below. Again, I know a lot of you guys don't actually have graphing calculators, so we're not going to like stress out about that right now. But I could go ahead and show you what that scatter plot would look like. That's going to be just taking each one of these values right here, the 2, 1.1, 0.605, 0.33, just graphing each one of these values right here. So let's go ahead and do that. So this would be 2. The next one would be 1.1. Next one is 0.605. This one is 0.33. Next one is 0.183. 0.101. 0.056. And 0.031. So you can see it's just kind of scrolling right on down this way. It's just getting smaller and smaller and smaller. And that's what we have right here for this graph. What kind of function might model the tennis ball bounce situation? Explain your reasoning with a table of values or other representation. Okay, so we have exponential decay. So let's say that's what we have here. Exponential, exponent, decay. Because we multiply uh, by 0.055. Oh, because we repeatedly multiply um, each output by 0.55 each time. That's where we get exponential decay. Exponential decay, which you've learned about in the past when you've done exponential functions in advanced algebra. When you do those, what you remember is that you're multiplying by the same value every single time over and over and over. It'd be exponential growth if I was multiplying by a number larger than one, but it's because it's less than one that I'm constantly multiplying its exponential decay, meaning that the function itself is going to be continuously getting smaller and smaller and smaller because it's decaying. It would be getting larger and larger and larger if it was exponential growth. Okay. And obviously, if I bounce a ball, it's not going to get higher and higher each time. It's going to get smaller and smaller each time. All right, look back at the table you generated in question 3. Write a function rule for bounce height in terms of bounce number. Graph the function rule with the scatter plot on your graphing calculator. See if the function rule models the data. Okay, so let's go ahead and look at that. If I look, where's here? Number 3. So we're going to go ahead and look at this table. And so what I'm going to do here, the function rule, remember the function rule kind of previously matched a linear function, so it's not linear anymore. It's now going to be exponential growth or decay, which in this case is going to be an exponential function. So I'm going to be taking this information here, and if you recall an exponential function, the way that you go ahead and set up an exponential function is it's normally y equals a times b to the x. So the b in this, that is your growth or decay factor. Okay. And then this A value right here is the initial amount. So knowing that information, if I was going to write this as a function rule, I would have y equals, and my initial amount here, so how high up was my initial drop amount, and that would be 2. So that's that initial amount, y equals 2. And then the growth or decay factor, so how much is it growing or decaying by? And in this case, it's 0.55, so I'm going to write this as 0.55 to the n power. I used n because that's what we're going to be using here. We're not using x. This is just a generic form for an exponential, but we're using n because we're using recursive functions here, and we're talking about an input of n values being whole numbers each time and all of that. So the way that I would write this here then would I'd also have to include n equals 0, 1, 2, 3, so on and so forth. And what is that initial amount, that h0? So h of 0 would be 2. Now again, I get that 2 right here from the 2 right here, which also matches the 2 right here in my table. That's where it's all coming from. Just like that 0.55 is that 55% from my bounce amount. And that's right here, that 55%. That rebound percentage is 55%. Okay, what is the height of the fifth bounce of a new tennis ball? If the initial drop height is 10 meters above the ground, use a function rule to find your answer. So instead of writing a table and going, okay, so let me go ahead and find, how all of this is going to work every single time and calculating out each bounce, that could take a long time. What if I asked you what the 17th bounce is? You don't want to have to figure out what the bounce percentage is for every single one from 1 through 17. That would be ridiculous. That would take forever. So instead, you want to create a function rule. So let's do exactly that. So the function rule, again, we're going to follow the same pattern of what we just did right above here. Okay, we just created this where it's going to be y equals. And remember that first number right here is going to be whatever that initial height is. Well, the initial height is 10. So this is going to be y equals 10 times the rebound percentage. How much is it going to change? Okay. And so what we're going to do here is we're going to use the same, and remember tennis balls, I'm trying to remember, what is it? 55%? Yes. So tennis balls out of the container have a 55% rebound percentage. So I have 10 times 0.55 to the end. There's my function rule. Okay. The only thing that I'm missing is that n equals, and so I'd say n equals 0, 1, 2, so on and so forth. And then I'd say my initial h sub 0 is equal to 10. And that's because that's that initial height. So I've got all of that. That's my function rule. How do I use that function rule? Well, I want to know the fifth bounce. So that means that I'm going to plug a 5 in for n, because remember the n is representing each bounce. So if I was wanting to know the 42nd bounce, I'd plug in a 42 right here and see what it says. So really, if I'm going to do this, I have y equals 10 times 0.55 to the fifth power. And the reason it's the fifth is because it wants to know the fifth bounce. So if I take 10, multiply it by 0.55 to the fifth power, that's going to get me back 0.503 meters. Okay. Suppose a new tennis ball is dropped from a height of 20 feet. How many times does it bounce before it has a bounce height of less than 4 inches? The diameter of the ball. Explain your solution. So all I'm looking for here is I've got to find my bounce height that's going to be less than 4 inches. And the reason that I want it is just because it's the diameter of the ball. So the way that I could do that would be just going ahead and trying each one of my inputs and seeing which one is going to get me something that would be less than 4. So I need to write a function rule. So just like this previous one, I'm going to write a function rule for this one. If you want to, go ahead, pause the video, try it on your own, make sure that you can kind of see how to come up with the function rule. So my function rule here, I go ahead, take that initial amount, okay? So it's dropped from a height of 20 feet. So there's that initial. So I have y equals 20 times. How is it changing? Okay. And again, this is a tennis ball, so it would be 0.55 because that's what our rebound percentage is for a tennis ball outside of the can. And then this is to the n power. And again, since I'm writing a function rule, I need to write it correctly. So it's n equals 0, 1, 2, so on and so forth. And then h sub 0, so my initial height is 20. So with that initial height of 20 and a 55% rebound percentage, this is what I've got. Now, I need to be really careful and notice how this question is worded. If you notice here, it wants to know how many bounces is it going to take before my ball is less than 4 inches. Notice my original one is given to me in feet. So be careful. So 4 inches in comparison to feet, that's something that we're having to kind of consider here. So the way that we would go ahead and do that is figure out, well, what is 4 inches out of 1 foot? So let's do that. Well, in this case, what I want to do is I want to go ahead and convert that 4 inches into feet so I know what I'm looking for. So let's do a conversion really quick. Um, I have 4 inches. Well, let's remember if I'm converting, and this is something that we did at the very beginning of last semester, and I know you've done it plenty of other times. If I've got inches on top, I've got to put inches on bottom to convert it. And feet. The reason I'm doing that is because I know how many inches are in 1 foot, and I've got to get rid of my unit, so I'm going to cancel out those inches, and that's going to leave me back with feet because feet are up on top. So no matter what you have, remember whatever unit you have with what you've got and you're trying to get rid of it, that means that you've got to put that same unit not in the same floor, if you want to call it a floor. So I'm on the top floor right now with inches right here with this 4 inches. And so that means that I've got to put inches on the bottom floor so that they cancel out. And I'm left with feet. And I think we can all agree that there are 12 inches in 1 foot. So that means I go 4 divided by 12. Well, that means that 4 inches is 1/3 of a foot, or also known as 0.333 feet. Okay, so now that's really what I'm looking for. That's that output value that I'm looking for, is that 0.33. So let's see, what does that look like? I'm through this in the calculator in Desmos right now just to kind of see what we've got. And so if I do my initial bounce here at 0 and it's 20 meter or 20 feet, then 11, then 6.05, then 3.3275. If you weren't careful and weren't paying attention, you would have thought that the answer here would have been 3 because that would have been less than 4. But remember, again, it was 4 inches, not 4 feet. So I've got to keep going. So I'm going to go 4 right here. Well, still not what I need. 5. Still not what I need. 6. Still not there, but close. I need 0.33. 7. There we go. So how many bounces does that take? Our initial bounce here was 20, or that was our original height, and our first bounce was 11, and then we got down to here, this 0.30. It take us 7 bounces. So all I was doing was plugging that into the Desmos calculator. You can do it the same just with a handheld calculator by plugging in this function in the handheld calculator and just continuously changing the number that you're putting in here. Plug in 1, plug in 2, plug in 3, plug in 4, plug in 5, plug in 6, plug in 7, and then you get the answer. So that's how you can do that. And so we would have 7 bounces. All right. All right, what is the total vertical distance that the ball from question 10 has traveled after 6 bounces? Explain your answer. Okay, what I just need to do is I just need to take all of the values that I have for each of these bounces. So that means that I need to take, when I plug in 0, 1, 2, 3, 4, 5, and 6 in here. So let's go ahead and do that. And created a table for you guys to just kind of see this. And all I did was just I took the equation itself and just plugged it in. This is exactly what you guys can do. And so that's all I did was I just took the equation, plugged in 0, 1, 2, 3, 4, 5, 6, and 7, and I got all of these. The reason I went ahead and did that was so that I had it all written down and I could go ahead and answer this question right here. Because it says, what is the total vertical distance that the ball from question 10 has traveled after 6 bounces? So the total vertical distance is going to be the sum of the 2 different heights that you're going to have. So the height of it going up plus the height of it going down. So if you kind of consider what you have here, if I was to go ahead and kind of think about it visually. Visually, what I'm trying to say here. So let me see. I just have this ball that I've got over here at 20. And that's where it's going to start, right? And I drop this ball down, hits down here, it comes back up, and it bounces, and then bounces, and then bounces. And that's what it's going to do. So I've got that. So that 20 is going to get here, and then it's going to go all the way down. So there's that 20, right? All the way there. But then it's going to come back up, hit this amount here, and come down. So you see right here, I go up the same amount as I came down on this blue one right here. So this is going to be counted twice, that height of 11. And then I'm going to do the same thing here. So this height that I'm going to have here, it's going to go up and down. It's going to go up and down that 6.05 twice. So basically what I'm doing is I'm just adding everything up, but I'm doing them twice. So I would do, in this case, 20, but I don't do that one twice because that one's only the one I'm dropping from there. It's coming down and then going back up. So I have 20 plus 11 times 2 because it does up 11, down 11. And then I'm going to have that 6.05 times 2. And then the 3.32 times, or 75, times 2 plus 1.8301 times 2 plus 1.0066 times 2 plus 0.55361 times 2 and then plus 0.30449. Now that amount right there, that 0.30449, I'm not going to add the 0.30449. And the reason that I'm not adding that is because that's the part that we're stopping, because that was that last bounce. So we're not going to be including that because that was the bounce that got us below the height of 4 inches. And so that wasn't a bounce that counted. That was the first bounce where it was below that 4 inches. And so we were coming down to this one right here because it's no longer traveling here. So I will go ahead, take all of those, add them all up together. And what I end up getting is 66.982 feet. That's my total vertical distance because vertical distance can be down and up. Now, down doesn't mean it's negative because it's still a distance. So let's go ahead and put this in here. So this would be that 66.982 feet. Okay, last question here. How can you decide if a data set can be modeled by an exponential function? How are recursive rules different from function rules for modeling exponential data, and how are they the same? So, anytime that you have a common ratio, meaning that it's being multiplied by something, not added by something, then you're going to have an exponential function. And that's where the differences between the linear and exponential are going to be really obvious. Because if my numbers are being added by the same number, then I have a linear function. If they are being multiplied or divided by the same number, then I have an exponential function. So that's what you're really going to be looking for. Now, how are recursive rules different from function rules for modeling exponential data? A recursive rule is where you're writing something based off of what happened previously. So, and I shouldn't say just previously, I should say the term immediately before. So that makes it so that it's very limited, just like we were discussing yesterday, that it makes it limited in terms of the usability. Because if I was wanting to know what is the height of the ball after the, I don't know, 26th bounce, well, that means that I need to know the 25th bounce. And in order to get the 25th, I need to know the 24th. So it's like you don't want to have to sit there and do all of that. That's what a recursive rule is. A function rule is where I can just plug in some value and get an output number. And so that's exactly what I did here with each one of these. So, and like, heck, even right here. So I used the function rule 20 times 0.55 to the n power. That was my function rule. And all I did was just plug in numbers and get these outputs. I could plug in with this function rule, go ahead and plug in, I don't know, 286 for n, and I would know what the height is at 286 pounds. Not really going to get a ball that's going to bounce that many times, but you know what I mean. It's got an input ability to just simply get an output. It makes it really easy for a function rule. They are definitely going to be the same because let's come up here and look at this. So, if where did it go? Oh, I thought that was here, right here. So if I look right here at this one, this is my recursive rule that I had. This is saying the next term is equal to the term before it times 0.55. And then it says right here that I had that initial term of 2, and I could have these n values increasing. So I could do that. My function rule for one exactly like this was right here, 2 times 0.55 to the n value. So it's taking that initial amount, multiplying it by the 0.55 to the n power. And that's just saying that I'm taking the previous term and multiplying it by 0.55. So they're very similar in that you're multiplying by the same number each time. But again, they're different because I can actually just take something and plug it in for n in this function rule and get an output and know exactly what the number is for that number term in my sequence. I can't do that with the recursive rule. So that's basically going to be the gist of the differences of what you're going to have here for the most important parts of what is going to be different. So I would say that as long as all of this makes sense, you should be good to go. If it doesn't make sense, then please send me a message, ask me questions. I know I'm not there, so just let me know how I can help you out.